Welcome back to Basic Electronics. In this class, we look at the use of Karnaugh maps or K maps in short to minimize a given logical function. First, we will see how a K map is constructed. We will then look at how to write the minimal form of a logical function from the associated K map. Finally, we will take up some examples in which the truth table of the logical function has don't care values. Okay, let us get started. We will now discuss minimization of logical functions, and a good way to do that is to use a Karnaugh map, or simply called the K map. What is a K map? It is a representation of the truth table of a logical function, and we will see several examples of a K map. A K map can be used to obtain a minimal expression of a function in the sum of products form or in the product of sums form. Now in our course we will mostly deal with the first one, the sum of products form, but once you understand how that is happening, you should be able to pick up very easily the product of sums K map as well. The question that we should ask ourselves is, what is a minimal expression? Here is the answer. A minimal expression has a minimum number of terms, and each term has a minimum number of variables. So that is what minimal means. The next question that arises is whether each logical function has a unique minimal expression or not. The answer to that is mostly yes, but for some functions it is possible to have more than one minimal expressions. Alright. Now why are we interested at all in minimal expressions? This is the reason. A minimal expression can be implemented with fewer gates, and that's why the implementation is cheaper. So let us look at an example of a K map now. Here is a logical function y of three variables a, b and c. We have ones here, 1, 1, 1, and we have one don't care condition here, and the rest of the entries are 0. Alright, so let us begin by drawing this map, and let us see what this means. This is C, and this means C is 0 here, C is 1 here. These correspond to the values of A and B. Here A is 0, B is 0, A is 0, B is 1, A is 1, B is 1, A is 1, B is 0. The next step is to map the logical function y from this table to this map. So let us do that. We will start with this one here. What are A, B for this entry? 0, 0. So that is this column here. What is C? That is 1. So it is this row here. So we are talking about this box. So this 1 will go into that box there, like that. What about this one? A, B are 0, 1. So this column, and C is 0. So this row. So we are talking about this box, like that. What about this X? A, B are 1, 0. This column. C is 0. So this row. So we are talking about this box. And this last one here. A, B are 1, 1. And C is 1. So this column and this row. So this box here. Like that. Now what about the boxes which are not filled so far? Those will get these zeros, and with that we get our complete K map shown here. Alright, let us now make a few observations. One, we observe that a K map is the same as the truth table. It has the same information except for the way the entries are arranged. Second, and this is a very important point, If we don't remember this point, then the results can be disastrous. So therefore we need to pay attention to this very carefully. In a K-map, the adjacent rows or columns differ only in one variable. For example, in going from the column AB equal to 0, 1, this one, to AB equal to 1, 1, there is only one change, and that change is in variable A. Similarly, when we go from 1, 1 to 1, 0, there is a change in B, only one change, and so on. Here is a K-map with 4 variables. So y is a function of A, B, C, and D, and here is the associated K-map. Let us see how this works. These values 0, 0, 0, 1, 1, 1, etc. correspond to A and B. These values correspond to C and D. And as we go from one column to the next, we notice, as we mentioned earlier, that there is only one change. For example, from 0, 0 to 0, 1, B changes but not A. From 0, 1 to 1, 1, A changes but not B, and so on. Similarly, as we go from one row to the next, there is only one change. Going from 0, 0 to 0, 1, D changes from 0 to 1 but not C, etc. Let us now look at the mapping of Y from this format to this format for a few entries. For example, consider this one. What are A and B? 0, 0. What are C and D? 0, 1. So we have AB 0, 0 and CD 0, 1. So we have this column and this row, and that is where that one goes. Let's take this X for example. We have AB equal to 1, 0 and we have CD equal to 0, 1. So AB equal to 1, 0 is this column and CD equal to 0, 1 is this row, and that is why we have that X over there, etc. You can check the other entries as well. Let us now look at a few examples of functions with one single term, such as this one here. So this is a single product term. It is the AND operation of A, B, C bar and D bar. And when is this equal to 1? It's 1 for AB equal to 1, 1 and CD equal to 0, 0. So that column and that row, that is where this one will appear. Alright, let us consider another product term, x2. Now this term has only 3 variables, A, C and D, and x2 is 1 if A is 0. That means 2 columns, because A is 0 here, A is also 0 here. So these are the 2 columns. And what is CD? CD would be 0, 1. That is this row. So therefore we have 2 ones now, like that. Let us take another example, x3 equal to A and C. This is another product term, a single product term. When is x3 equal to 1? When A is 1 and C is 1. A is 1 in these 2 columns and C is 1 in these 2 rows, and therefore we have 4 ones here. Alright. Now let us make a few observations which are related to functions of this type, where the function is a single product term but with different number of variables. Here we have 4 variables, here we have 3 variables, here we have 2 variables. Here is a table which relates the number of variables in these functions and the number of ones which appear in the K-map. If we have 4 variables, as in this case, then we have 1, 1 there. If we have 3 variables, like in this case, then we have 2 raised to 1 ones, that is 2 ones, like that. and if there are two variables, as in this case, then we have 2 raised to 2 or 4 ones in the K-map, like that. So in each of these cases, the number of ones is given by a power of 2, and that is a very important point to remember. Alright, so that was about the number of ones, and now we want to talk about the position of these ones. How do these ones appear in the K-map? And if we look at these examples, we realize that the ones can be enclosed by a rectangle in each case. So here is a rectangle, here is a rectangle, and this of course is just a single entry. Now these ones appear adjacent to each other and not one here and the other one here, so that we can form a rectangle around these two entries. And the same thing holds about these 4 ones as well. So that's a very important point as well. Let us look at these same examples once again and summarize the points that we made in the last slide. If we have a function which is a single product term, as in all of these, then we can make 2 points about the K-map. Point number 1, the number of ones is given by a power of 2, 2 raised to 0, 2 raised to 1, 2 raised to 2. And point number 2, the ones are positioned such that we can draw a rectangle around them. Alright, now with these in mind, let us proceed further. Let us now consider a function y, which is the sum of x1, x2 and x3, that is the OR operation of x1, x2 and x3. What will the map of y look like? Y is 1 if x1 is 1, or x2 is 1, or x3 is 1. So all we need to do now is to look at the position of ones in these 3 maps and just replicate those ones in the map for y. It's as simple as that. For example, this one will go here, these 2 ones will go here, and these 4 ones will go over here. And that gives us the map for the function y. Alright, we now come to the actual problem that we are interested in. We are interested in identifying a minimal expression from the given K-map. So take this y as an example. We are given this map, and from this map we want to find the minimal expression for the function. And what do we mean by minimal? We must have the smallest number of terms and smallest number of variables in each term. That means we must identify the smallest number of rectangles containing 2 raised to k ones, each as large as possible. Let us see what this means in the context of this particular example. Alright, so this K-map is given to us and we are asked to find the corresponding minimal expression. How do we go about it? We first identify rectangles which contain only ones and no zeros, such that the number of ones is a power of 2. So we identify rectangles with 2 ones or 4 ones or 8 ones and so on. Alright, now we know that for each rectangle we can write a product term. We have not yet looked at how to do that. So there are 3 terms because we have 3 rectangles here. This is of course a rectangle containing a single term. So one rectangle, second rectangle, third rectangle. So we know from this map that we have 3 terms, and then we proceed to write each of these terms, and that gives us the minimal expression. So let us do that for a few examples and then it will become very clear. So here is our first example, and we want to find the minimal expression for this logical function y given by this K-map. So what is the first question we ask? We want to find out how many ones are there, and we see that there are 2 ones and in this case they happen to be adjacent, so we can have one rectangle covering these two ones like that. And since there are 2 raised to 1 ones forming a rectangle, we can combine them. Since the rectangle covers all the ones which are in the K map, these two ones, we can conclude that the logical function y is represented by a single product term. The next question is, what is that product term? Let us make a few observations. 1. The product term is 1 if b is equal to 1 and c is equal to 0. And we can see that from the K map. These are the two ones which are covered by our product term. For this one, the value of b is 1. For this one also, the value of b is 1. What about c? In both these cases, c is 0. And that is why we say that the product term is 1 if b is equal to 1 and c is equal to 0. That is our first observation. Second, the product term does not depend on a. And we can see that from here. The product term is 1 if a is 0. It is also 1 if a is 1. So clearly it does not depend on a. So the only product term which satisfies all these conditions is b and c bar. This product term is 1 if b is 1 and c is 0, and it does not depend on a. And since in this case this product term represents the logical function y, we can say that y is equal to bc bar. And we can see that from here the product term is 1 if a is 0. It is also 1 if a is 1. So clearly it does not depend on a. Alright. Now it turns out that the only product term that satisfies all of these conditions is b c bar. bc bar is 1 if b is 1 and c is 0, and bc bar does not depend on a. And in this specific example, the product term that we have figured out is the logical function y itself, because as we mentioned earlier, y has a single product term because this one single rectangle covers all the ones in the K map, and therefore we conclude that y is equal to b c bar. Next example, once again we have two ones here, this one and this one, and the question is whether we can combine these two. The answer is, although the number of ones is a power of 2, they cannot be combined because they are not adjacent, that is, they do not form a rectangle. The only rectangle we can think of which will contain these two ones is this one, but then in that case it will also contain zeros, and that is of course something we don't want. So then we have a function with two terms which cannot be combined, and each of them is a min term. What is this min term? It is 1 when a is 1, b is 1 and c is 0. So it is a, b, c bar. What is this min term? It is 1 when a is 1, b is 0 and c is 1. So it would be a, b bar, c. So our function then is this term plus this term, like that, a, b, c bar plus a, b bar, c. And it cannot be minimized further. Next example, once again we have two ones, one here and one here, and the question is whether these two ones can be combined. Now it seems to us that we cannot draw one rectangle without also including these zeros to contain these two ones that we have. And so the answer seems to be that the ones cannot be combined. But let us redraw this K map by changing the order of the columns in a cyclical fashion and see what we get. Here is the revised K map, and what we have done here is we have drawn this 1 0 column first, followed by 0 0, then 0 1, and then 1 1. So 0 0, 0 1, and 1 1. And these two entries 1 0 have gone here, these two entries have gone here, and so on. So by doing that, we are not really changing the function. The function is still what it was. All we have done is rearrange the entries in the K map. And now we see that these ones have come next to each other. So the two ones are in fact adjacent and can be combined like that. And what is the term that corresponds to this rectangle? That is easy to figure out. We know that that product term is 1 if B is 0 and if C is 0. And it is independent of A because A is 1 here and A is 0 here. So that term must be B bar C bar. In other words, columns AB equal to 0 0 and AB equal to 1 0 in the K map on the left are indeed logically adjacent. So these two columns 0 0 and 1 0 are logically adjacent. And what does it mean? That means if we go from this column to this column, there is a change only in one variable. So A is changing from 0 to 1, but B is not changing. So therefore these are logically adjacent, although they are not geometrically adjacent. And we could therefore have combined these ones without actually redrawing the K map like we did here. As long as we know that these two columns are adjacent, logically adjacent, we can think of a rectangle which covers this one and this one. Let us take this example. How many ones do we have? 1, 2, 3, and 4. And it appears that these 4 ones are not adjacent to each other and therefore cannot be combined. But they actually are adjacent. And why is that? Because this column is adjacent to this column, logically adjacent. Similarly, this row is adjacent to this row. And therefore it is actually possible to draw a rectangle which will cover all of these 4 ones like that. And you are definitely encouraged to redraw this K map so that these 4 ones will appear as a bunch. Okay, so what is the term that corresponds to these 4 ones? That product term is independent of A because A is 0 here and A is 1 here. It has B bar because B is 0 here and B is 0 here. It is independent of C because C is 0 here, C is 1 here, and it contains D bar because D is 0 here, D is 0 here. So that product that we are looking for is X equal to B bar D bar. Another example, once again we have 4 ones, 1, 2, 3, 4, and we can think of a rectangle which can cover these 2 ones, another rectangle which can cover these 2 ones. So our function can be written as a sum of 2 terms, one corresponding to this rectangle here and another corresponding to this rectangle here. But we can actually do better than that because this column 0 0 is adjacent to this column 1 0, and in fact these 4 ones can be combined with a single rectangle like that. And what is the term that corresponds to this rectangle? It must be independent of A because A is 0 here, 1 here. It must contain B bar because B is 0 here. It must be independent of D because D is 0 here, 1 here. And it must contain C bar because C is 0 here. And that gives us B bar C bar. Let us now consider this example, which brings out a very important point. We have 3 ones here. this one corresponds to A, B, C bar, D bar, this first term here. This one corresponds to A, B, C bar, D, this second term, and the third one to A bar, B, C bar, D, the third term here. Alright, now since we have only 3 ones and 3 is not a power of 2, these ones cannot be combined into a single term. However, they can be combined into 2 terms, and let us see how. We can in fact have 2 rectangles, one like that and one like that, which will cover these 3 ones. But then notice that this one is getting covered twice. Now, is that okay? Let us check. Let us write x1 as AB C bar D bar plus AB C bar D, and we will write this term twice. So AB C bar D plus AB C bar D, and then this term. Alright, now these 2 terms have A, B, C bar common, and then we get D plus D bar, like that. And these 2 terms have B, C bar, D common, and then we get A plus A bar. Now this is 1, this is also 1, and that gives us this minimal expression A, B, C bar plus B, C bar, D. And we don't need to actually go through this algebra. We can simply do this by inspection. We can draw 2 rectangles, one to cover these 2 ones and another to cover these 2 ones. And it appears that we are covering this one 2 times, but that is okay, and that is because we have used this identity here. This term, call it y, we have written as y equal to y plus y, and that is perfectly fine. One more example. These 4 ones here can be clubbed into a single term. These 2 ones can be combined with these 2 ones here, because this column and this column are logically adjacent. What will happen if we combine only these 2 and not these 4? This rectangle would have only 2 ones, and that will mean a product term with 3 variables, whereas this rectangle, the purple one, has 4 ones in it, and therefore that gives us a product term with 2 variables. So we save 1 variable in going from 2 ones to 4 ones. Alright, now this one cannot be combined with any neighbor, and therefore that remains as a minterm. This one is adjacent to this one, because this row and this row are logically adjacent, and therefore we can combine that one with this one. Notice that some of the ones have been used multiple times, and like we saw earlier, we can do that because of the identity y is equal to y plus y. For example, this one has been used in the pink rectangle as well as in the purple rectangle. This one has been used in the purple rectangle as well as in the green rectangle. We can use ones multiple times, and what is the overall objective of this whole exercise? We want to cover all the ones in the K-map with the smallest number of rectangles. That gives us the smallest number of product terms in the final minimal expression, and with each rectangle as large as possible. And what does that do for us? That gives us product terms with a smaller number of variables. So that is how we get a minimal expression. Now let us see what the minimal expression corresponding to these rectangles is. There. This term, for example, A bar C bar, corresponds to this green rectangle here, and you should really verify that. So we have four terms in the minimal expression, one corresponding to the green rectangle, one corresponding to this purple rectangle, this one corresponding to this yellow rectangle, which is just a single min term, and one corresponding to this red rectangle, that one. So that is our final minimal expression. Let us look at this example which has some don't care conditions. There is a don't care condition here denoted by x, and there is another one here. Now the question is, what do we do with these x's? We can make this x 0 or 1. Similarly, we can make this x 0 or 1. And the question is, what would be a good choice? Let us see. Suppose we make this x equal to 0 and this x also equal to 0. What do we have then? Then we have this one here, this one here, this one, and this one. We have 5 ones. These 2 ones can be combined with a rectangle. These 2 ones can also be combined with a rectangle. This one is actually adjacent to this one here, and therefore these two can be combined as well. So we have 3 rectangles, that means 3 product terms in the final expression, and each term will have 3 variables. So that is the situation, and it turns out that we can do better than that, and let us see how. Let us suppose that we make this x equal to 0 and make this x equal to 1. And now we find that we have a much better situation. These 2 ones can be combined with one rectangle, and these 4 ones can be combined with another rectangle. And with that, we have only 2 terms in the final expression, CD bar plus A bar C bar D. And that definitely is a better choice than our first choice, in which both x's were zeros. So when we have don't care conditions in a K-map, we need to consider various possibilities and choose that possibility which gives us the minimal expression. In summary, we have learned how to use K-maps to minimize logical functions. We will find this technique very useful in subsequent topics. That is all for now. See you next time.